Hello everyone, welcome to Unacademy guys, and yes, this is another video of name reactions. So I'm posting after a very long time, I know this, but I hope that you have visited all the other name reaction videos that I have already posted. So I posted till 39th name reaction and this is our 40th. We are starting with very important 3 Sigmatropic name reaction series. So first of all, we'll start with the Claisen rearrangement, and along with that there are other very similar name reactions which you might get confused if you don't know them already. Okay, so we will be talking about these very important name reactions today. So let's begin very quickly. When the name reactions are done, we will be solving some important previous year questions as well. Okay, alright, so the Claisen rearrangement is what we are going to study first of all. So here we are: Claisen rearrangement, Para-claisen rearrangement, Eschenmoser Claisen rearrangement, Ireland-Claisen, Johnson-Claisen belong to the category of 3 Sigmatropic rearrangement. Okay, so these are all different name reactions, although the mechanism is very similar. Alright, so let's talk about this. That what do you require when you look at a molecule? How are you going to identify that 3 Sigmatropic reaction is possible? So first thing first, you can just look at the allyl vinyl ether system. Alright, so what is the allyl vinyl ether? This oxygen, when it is present at this carbon, which is an sp2 carbon, here it is an sp2 carbon, here it is an sp3 carbon. Alright, so this system would be called as the allyl system, and this system is the vinyl system, and the oxygen makes the ether. So it is the allyl vinyl ether system that you have to identify first of all for the Claisen rearrangement to happen. And you do the numbering always from the saturated carbon. So 1, 2 and 3, 1, 2 and 3 like this. Do the movement of bonds in this manner, and then you get a transition state like this, and further your alpha, beta, gamma and delta. Gamma, delta, unsaturated, aldehyde or ketone depending on the substituents. Okay, so this reaction is very simple. Now what could be the variant of this reaction? If the stereochemistry is asked in this reaction, that would be very important part. And how do you do that actually? So you write the same thing into a 6-membered ring formation. So basically, let's say there is the oxygen over here. Let's say this is our carbon number 1. So 1, 2 and 3, there is a bond like this. 1, 2 and 3, there is a bond like this. Okay, so you will draw a 6-membered transition state to be able to understand the stereochemistry. Always, as much as possible, we try to keep this R group, if it is an alkyl group, on the equatorial position like this. Above there is nothing, it is just our number 1, there is nothing. Okay, so move the bonds in this manner, you get a double bonded oxygen like this, and the R is trans. So basically what just happened, you are having a trans alkene, or let's say an E alkene, and your double bond. Okay, so you will be able to tell the stereochemistry of the product with respect to if there was any group on this carbon, then also it is predictable on this carbon, predictable on this carbon, it is going to lead to the alkene formation, E or Z alkene, that also is predictable. Okay, so very simple reactions. Now this is an example. If you want, you can just do this by yourself after stopping the video. So it's a very simple one: 1, 2, 3, 1, 2 and 3. So once again we gave the numbering on the saturated carbon first like this, then you move the bond. So I would rather write this phenyl ring in this manner, so that the movement of bonds is very easy actually. Okay, yes, 1, 2, 3, 1, 2 and 3. So now move the bonds, 3 Sigmatropic rearrangement in this manner. So you will have a double bond to this phenyl ring and a new carbon-carbon bond formed like this. Okay, and over here you have a double bond like this one. Carbon number 3, carbon number 2 and carbon number 1 3 2 1 if you want me to write. This is your carbon number 3 oxygen, and rest of the molecule is like this. Okay, so this is your rest of the molecule. Alright, so this is your final product after the 3,3 sigmatropic rearrangement over here. Right, so what just happened, guys? You just, again, here you don't have the allyl vinyl ether system, but you have the allyl, and you also have the phenyl ether system. So it is the allyl phenyl ether system that you have at this temperature. In the presence of Lewis acid, guys, you don't require heating and so on. Right, when there is no Lewis acid, then you have to provide heating, but when there is Lewis acid, the reaction could also be carried out at very low temperatures as well. Okay, so this is your 3,3 sigmatropic rearrangement, but when it is happening in the allyl vinyl ether system or your allyl phenyl ether system, alright, then it is called the 3,3 sigmatropic is called the Claisen rearrangement. Similarly, guys, let's talk about one more, your Para-claisen rearrangement, and this has been asked a lot of times in your CSIR NET exam or in your GATE exam, right? So it's a very beautiful reaction. Let's see. So what is it? Further rearrangement of the normal ortho-claisen rearrangement product gives the Para-claisen rearrangement product. So what is it talking about? So ultimately, if let's say again you have the phenyl allyl system, so this is your allyl and phenyl ether system, but you have a substituent on the ortho position, so the reaction cannot just stop on the ortho position, right? So if it cannot stop on the ortho position, it will finally do one more rearrangement and then it will give you the para product, hence the name Para-claisen rearrangement. Let's talk about it. So guys, here you have substituents on both the sides of the benzene ring. Now if you don't have substituent on both the sides, if it is there only on one side, then the reaction takes place from the other side. That's obvious. Okay, so let's do the numbering 1 2 3 1 2 and 3 like this. So this is how you are going to move the bonds, right? So the intermediate first of all is going to be your double bonded oxygen like this, and so there is a new bond which is formed over here. You don't need to talk about stereochemistry as such because it is not stopping over here. Further there will be a reaction. So it is like this, I guess, 1 2 and 3. Alright, so 1 2 and 3, or let's say 3 2 and 1. So this is 3 2 and 1 like this. So this is your intermediate actually, because now the rearomatization cannot happen, the R group cannot be lost, this cannot be lost, hence you will again move onwards and see a possibility of the cope rearrangement. Now we won't call it Claisen rearrangement because there is no more oxygen over here. Let me just rearrange the molecule in a way so that we understand and very clearly see. Alright, so very clearly we are able to see that 1 2 3 1 2 and 3. Now this 3,3 sigmatropic rearrangement will be called as the cope rearrangement, not the Claisen rearrangement, because there is no oxygen. Okay, so this is how the reaction happens. And finally, alright, so there is R group on both the sides now, and yes, there is a double bond over here, and finally you have something like this. Okay, so right now finally on this carbon you have a hydrogen which can undergo rearomatization like this to give you the final phenol, which is also stable in because it is aromatic, right? So moving back into this molecule, see, why did we not go on to some other product formation? Because here you have a hydrogen which could be lost directly and to give you this product. Alright, so there is no more rearrangement possible over here because directly you are getting this OH group now, and yes, this is it. Okay, finally, so this is your product. Now further, Here it happened because on the ortho position there was no hydrogen to be lost, and that is why the molecule is looking at more stability, hence it has to carry out one more 3,3 sigmatropic rearrangement after this. Okay, and then do the rearomatization by the loss of this proton to give you this final product, hence the name Para-claisen. So further rearrangement of normal ortho-Claisen rearrangement product gives the Para-claisen rearrangement. Okay, very well. So we have done two Claisen rearrangements till now, and we move onwards to the third one, that is Johnson-Ester Claisen rearrangement. So basically here we are going to come across the orthoesters, that is your trialkyl orthoacetate. What is it? So trialkyl OR orthoacetate is something like this. Alright, and in the presence of, you also often call it orthoester, in the presence of an acid, a trace amount of weak acid gives a mixed orthoester. So that is your product. If you are starting with this kind of allylic alcohol, this is allylic alcohol, right? Allylic alcohol if you are starting with, and you are making it react with this kind of a trialkyl orthoacetate molecule in the presence of acid, after the 3,3 sigmatropic rearrangement, it gives you this final product which is a ester. Okay, so we can directly call it Johnson-Ester Claisen rearrangement, so that you remember that what is the product which is formed. So guys, first of all, from the allylic alcohol we are going to make such a molecule which may help you in doing the 3,3 sigmatropic rearrangement. So first of all, it is just like the acetal, so the hydrolysis of acetal takes place in the same manner. Alright, I hope that you can write the acetal hydrolysis mechanism. Here I am just pushing this bond off at once. Okay, the bond is going to actually take away the proton and loss of alcohol. Directly I am writing over here. Okay, so this is your oxonium ion which is generated. This oxonium ion is, further it is attacked OR positive and OR like this. So the oxonium ion is further attacked in this manner. Alright, and your oxygen, carbon, this is the OR group and another OR group, for example. Alright, so this is what you have. Just a second. CHOR whole thrice. Yes, one of the bonds moved away. CH bond connectivity is the same. Now the oxygen will want to push away one of the oxygens in this manner. Alright, then you would directly have something like this, R dash, and there has to be one CH3 group, right? Directly it is not going to have something like this. It must also have a CH3 group, I guess. So two of these ester groups and one CH3. Yes, that is what is required. That is going to help the reaction. So if I write CH3, OR, or let me just write once again, CH3, OR, and OR over here, that is going to help in the ester hydrolysis. So, right, so now it is going to take away the proton. You have CH3, carbon, and oxonium ion, OR positive, right, like this, and further this alcohol can actually attack over here to give you something in this manner. Alright, so attacked on the carbon, the bond opens away. There's a CH3, there's an OR and another OR in this manner. So the oxygen once again attacks and removes the other ester group. other alkoxy group and a double bonded oxygen. Yes, this is perfect. Now you lose a proton from this side, and the oxonium ion once again comes back for the formation of your similar molecule, that is the allyl vinyl ether system, just that you also have an extra OR group over here. So this is what you have to synthesize. So ultimately there is going to be 3 of these and not the hydrogen. There is going to be a CH3 over here because you require the alpha proton for the loss of the proton and the creation of this allyl and the vinyl ether system. Okay, I hope that you realize this is your allyl and vinyl ether system once again. Now the rest of the reaction is very simple. You can just carry out, just make some sections. So now you can just carry out your 3,3 sigmatropic rearrangement because this is very easy now. CH2 OR R dash. So here it is. R dash once again. So it is CH2 C double bond O and OR like this. So what do you see in the product? Is this your product directly? Is this your product which I have drawn over here? Yes, exactly. So Johnson-Claisen rearrangement, first of all, it's very easy guys. You have to take the excess of trialkyl orthoacetate. So this is your trialkyl orthoacetate. You have to heat it in the presence of acid and your allylic alcohol to first generate the allyl vinyl ether system. Then you do the 3,3 sigmatropic to directly get the ester molecule. So in the Johnson-Claisen rearrangement, we are getting the ester. Similarly, right, you have CH2 COOR, CH2 COR, right, perfect. Similarly, in the Eschenmoser Claisen rearrangement, which is our 43rd name reaction. So in this reaction, you are forming the amide. So Eschenmoser Claisen amide rearrangement, we can also call it formation of amide through amide acetal rearrangement. Now exactly the same thing that we have seen previously. There you had the trialkyl or trialkoxy molecule. Here you have the amide like this, acetylamide. So once again in the presence of proton or acid, it is going to generate, this is a CH3 once again, right? It is going to generate the iminium ion like this, right? And further the alcohol attacks to open up the bond and you get something like this. There is this. Always write the whole mechanism, that will give you a nice clarity upon what is happening. So this oxygen attacked over this carbon, okay, and NMe2 bond has opened up. This is your CH3, this is your OMe once again. So this oxygen attacks and removes the methoxy with a proton. Ultimately that leads to the formation of this molecule. Then there is NMe2 and then there is CH3. Loss of a CH3 proton would give you something like this. Now a CH2 and NMe2. So what just happened? First of all, acetylamide hydrolysis happened. The allylic alcohol has attacked to generate the allyl vinyl ether. Once again, this is your allyl and this is the vinyl ether system, just that you have a amide or you have a nitrogen. So this 3,3 sigmatropic rearrangement now is directly going to give you the amide. Okay, so it is directly going to give you the amide. Let's continue in the next page also. Right, so this is what you have, R dash and CH2 single bond, C double bond O and Me2. So this is exactly what the amide looks like. Alright, so it is your formation of amide through amide acetal rearrangement. Once again the same thing, through the amide acetal rearrangement like this. We are doing the rearrangement, and this is your amide, hence called the Eschenmoser amide-Claisen rearrangement. Okay, so this is our third variation of the fourth variation of the Claisen rearrangement, and our last one, the fifth variation of Claisen rearrangement, is Ireland-Claisen rearrangement. Yes guys, we have so many name reactions under just one canopy, that is your Claisen rearrangement. So last but not the least, you will have also seen this reaction many a times in your CSIR NET exam. So it is rearrangement of allyl trimethylsilyl ketene acetal prepared by reaction of allylic ester enolates with the trimethylsilyl chloride to yield the gamma delta unsaturated carboxylic acid. So lot of language, let's directly jump onto it. That you have a molecule like this. This is your ester already. Now the ester is a little bit different. Why? You just have a methyl group, so it is some kind of acetate through which the oxygen is connected to the allylic system and the ketone part is connected to a CH3, or let's say any enolizable carbon. Okay, this is an enolizable carbon that we have to keep in mind. So in the presence of LDA, which proton is going to be removed? Definitely the enolizable alpha proton. So that alpha proton, it got removed, and you know what the LDA does is LDA can remove any of these protons, right, and then it would give you an enolate. Enolate is going to attack over silicon, Cl gets removed and the enolate is fixed over there. So this is how your enolate gets fixed right over here. Okay, and what does it make? It makes once again the allyl and vinyl ether system once again. So you do the 3,3 sigmatropic rearrangement in this fashion, and this is once again going to be alright. So this is once again going to be your Claisen rearrangement, and I would write OSIMe3 over here. Okay, because one of the oxygen silicon bond is still intact and just a double bond O has formed with a new carbon-carbon bond like this. Okay, so this is how the molecule looks like after hydrolysis. After hydrolysis, you get the acid. Okay, so many Claisen rearrangement reactions. We actually have the Johnson-Claisen giving you the ester, we have Eschenmoser Claisen giving you the amide, and we have Ireland-Claisen giving you the acid. Okay, all of these are gamma delta unsaturated carbonyl molecules. Okay, now so we are directly going to jump on to your previous year questions. So this is one of the previous year question, that is major product formed in the following reaction is. So it is a CSIR NET question, I guess in 2018 or 19, somewhere over there, right? So right, what just happened? What do you see? You see LDA and you see TBDMSCl, so that is tertiary butyl dimethylsilyl chloride. Okay, so this is your TBDMSCl, and you know just by looking at LDA and the trimethylsilyl or tertiary butyl dimethylsilyl that it is Ireland-Claisen. It is Ireland-Claisen rearrangement. Okay, isn't that easy? Alright, yes it is. So first of all, you are going to figure out that this is how your molecule looks like, TBDMS. Alright, this is how the molecule looks like. And guys, you are directly not having any 3,3 sigmatropic over here. Why not? Because this portion is okay. It is your vinylic system, but this is also vinylic system. You don't want vinylic, you want on the other side allylic system. Hence, first of all, you are going to do heating with this. That is your CO2Me. This is a dienophile actually. It is a dienophile. You are first of all going to do 4+2 cycloaddition, and followed by that you carry out the 3,3 sigmatropic. And be very attentive while doing the stereochemistry. The CO2Me group goes endo because of endo selectivity, deals all the reaction. This hydrogen is above, and the other hydrogen which comes over here, this carbon, that also is above because the ester goes below due to endo selectivity. And the final product that you do, alright, so it is always going to be a major 1,2 product, right? Alright, so it is going to be like this. After there is a bond formation, the hydrogen which was present, it is above the plane, and once again the CO2Me is below the plane, right? This is how it happens. Okay, now where is the double bond? The double bond is right over here. Now do you see any sigmatropic possibility over here? It is 1, 2, 3, 1, 2 and 3. Now it is possible. Yes, now it is possible. So you just bring onwards. You can just, okay, so just take care the hydrogen is below, the ester group is also below, or the hydrogen is above and the ester is below, which means that this oxygen is also reacting from below the plane itself. OTB, DMS, and so on. So your 3,3 sigmatropic rearrangement that happens, it gives you an acid for sure, it gives you an acid only, but what is the position now? The position is right over here, to which your new carbon chain is going to attach, and that also from below the plane. So ultimately the product looks like this, CO2Me. It is from below the plane, so your other group also must be below the plane. So this is how it happens. And you have CO2Me after hydrolysis. Okay, so after hydrolysis you have this reaction, you have this final product. So your answer is option number C. Okay, so first of all, it is the 1,2 major product. In the Diels-Alder reaction, always the 1,2 and 1,4 are more preferred. The stereochemistry I have already explained lot of time in my special classes and plus classes also on Unacademy Plus. If you are having any doubt, we can discuss that in another video. And this is your molecule that you are getting. 1,2 product you are getting major. After that, 3,3 sigmatropic gives you this molecule. Alright, very simple one. Let's talk about the other. 96. Alright, so major product formed in the following reaction is, we have done this several times in our Unacademy classes. So before the exam also I've told you how to figure it out. Just very simply draw the 6-membered chair conformation. Draw the 6-membered chair conformation. For example, the methoxy is written below. Let's take it on the equatorial position. OH is written above. Let's take it once again on the equatorial position over here. So it is 1, 2 and 3. So there is a double bond like this, and there is a double bond, another one over here. So since it is a 6-membered ring, I'm just drawing it plainly over here like this. O is above, this O is below. Both of them are equatorial. After drawing, okay, so there is a trans alkene, the substituents which is present is trans, right? So okay, very well, you do this reaction. Okay, and your methoxy once again goes below the plane. It is very important to identify the stereochemistry of this new double bond, this which has formed, because you see that the methoxy is below the plane and this bond is already above. So it has to be a trans alkene once again. It has to be a trans alkene once again, and this methyl, since it was trans, it is now below the plane. And be very careful of it that OH bond was present above the plane, so which means that this carbon-carbon bond is below. The whole 3,3 sigmatropic reaction has taken place from below the plane. Once again, the hydrogen which is present on this carbon, it is above. So this is your major product of this reaction. Always try and form the 6-membered ring in this manner. 1 2 3 1 2 3. Always try and form the 6-membered ring. It would be very easy to answer. दूसरी चीज़ कि if we are paying attention that this side OH has above the plane, then this side, even if the carbon is planar right now, but later on, yes, later on it could go above the plane because the whole reaction takes place from below. So your answer is option number C, and the bond is, for sure, it is going to be E in nature. Alright, so your answer is option number C for this question. We have done very good questions, guys, and we have done 5 name reaction: your Claisen, Para-claisen, Eschenmoser Claisen, Johnson-Claisen and Ireland-Claisen reactions. If you are liking my content on YouTube channel, you can also watch my free classes. So every month I'm conducting a lot of free classes. If you want, you can see the free classes live or you can watch the recordings. And also don't forget to follow me on Unacademy, because that makes sure that you are having regular updates and notifications about all the classes. Okay, and if you are thinking of joining Unacademy Plus, then don't forget to use this code JAGRITIS. Alright guys, we'll see you very soon. Have a nice day, and yes, keep studying, keep practicing.